Okay, so we're going to pick up where we left off yesterday. And start by looking at a mean fill example. I think there's a typo in the notes, because it's talking about 32-ounce cans of beer, but yet at the bottom we're talking about 16-ounce cans of beer. So I think there's a slight typo here.
Do we need our Z-chart and all that?
Yes. And yes, you heard right. Not root beer. Beer. Okay, so we would like to compare the mean fill of 32-ounce cans of beer from two adjacent filling machines. Past experience has shown that the population standard deviations of fills for the two machines are known to be sigma 1 is equal to 0.043 and sigma 2 is equal to 0.052 respectively. A sample of 35 cans from machine 1 gave a mean of 16.013, and a sample of 31 cans from machine 2 gave a mean of 16.009. Determine if there is convincing statistical evidence that the mean fill of 32-ounce cans are the same for the two machines. Use a significance level of 0.05. Okay. What do they want us to test? To see if they are what? The same. So that right there should give you an idea as to which hypothesis we could do first. So what should this be? The null or the alternative? If we want them to be the same, which means we want them to be equal.
No.
That's the null. Okay, let me go to a screen where I have room to write. So if we let mu1 be the mean fill for machine 1, mu2 is the mean fill for machine 2, then our hypothesis, we said, is for them to be equal. H0 is that mu1 equals mu2. What would that mean our alternative would be then? That they're not equal. Now keep in mind the problem claims that they are equal. So this top one is our claim. Another way to write these, though, that way we have a hypothesized value, would be in that manner. mu1 minus mu2 is 0. And then, I don't know why they wrote it like this. I mean, that's the same thing we wrote. You should say mu1 minus mu2 is not equal to 0. That's another way we could write it.
And why is it equal to 0?
Because we want them to be the same.
Okay.
We want them to have no difference. Okay, so just on this example, at least a few quick comments about the example itself. Mainly the assumptions. We'll see some writing though. So I'll kind of get ahead but not advance the next slide, if that makes any sense. So let's look at our problem. What do you notice they tell us that we usually don't know? Sigma. So which test would we be able to use since we know sigma? Z. This example is just to get us practice doing a Z test. Take it just as that, as practice. Typically, I say typically, the credit has a whole assignment where you know sigma. But in real life applications, you typically do not know sigma. So this is just getting an example to get us practice.
So,
Yes.
we do or don't know sigma in this?
We do.
What does it say in here? The population standard deviation?
Yep. That's right.
Oh yeah, I see that there. Sigma.
So since N1, if you also notice, N1 and N2 are both large. They're both greater than 30. We don't really need to make any assumptions about the nature of the distribution. We don't need to say they're normal or anything like that, because why? Sample size is large, but what theorem helps us to say that? Close. Not central value. What's the L stand for? Limit. Central limit theorem. The central limit theorem allows us to say, okay, it's greater than 30, it's going to be approximately normal. Again, this example is a bit of a stretch, since knowing the population standard deviation without knowing the mean is pretty unusual. Accept this example for what it is. It's just a sample of the calculation. And generally, we're going to use this dealing with what-if type of scenarios. And we'll move on to another technique that is somewhat more commonly used when sigma is not known. Anyways, we actually already saw it yesterday. We saw that technique. That's where we had to do that big old fancy degree of freedom formula, which I found out dual credit you don't have to know.
When we did yesterday with the degree of freedom, you don't have to know?
Yeah, I don't have to know it. I'll talk about it when we get to that point, but you will have to know. Okay, so on this one, let's do a calculation here. So we need to get our test statistic next. We remember from yesterday, okay, where did my pen go? There it is. Z is equal to x1 bar minus x2 bar minus mu1 minus mu2 over, and we have our big old standard error, standard deviation, whatever you want to call it. Sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, so what was the mean for the first machine? What did it say the mean fill was for the first machine? 16.031 minus the mean fill from the second machine. Yep. And then what do we want our difference to be? 0 over standard deviation of machine 1 is 0.043 squared over sample size of machine 1, 35, it looks like, plus standard deviation of machine 2 squared over 31. Don't forget to square your standard deviation. If we calculate that statistic, what would we get?
You did minus 0 because we're trying to set it same.
And as soon as someone gets what they think it could be, let's go on and just say it, and I can say yay or nay. So the 2 decimal places, 1.6. Just to keep it moving, see how far, see if I can get further than I did last period. Okay, so 1.86 is our test statistic. Now let's get the p-value. Now what kind of test is this? Is this one-tailed or two-tailed? Two-tailed, we have not equal. So we're going to need to do 2 times the probability that z is greater than 1.86.
Could you also do less than negative 1.2?
Yes, that's what I was just about to say. That way we don't have to worry about 1 minus. We could do 2 times the probability that z is less than negative 1.86. Thank you. Now let's look at our z table for negative 1.86 and see what probability we get. .0314. 2 times that gives you 0.0628. Okay, so what was our alpha in this case? Alpha is 0.05. Which one is smaller? Alpha. Let's write our conclusion here. Since p-value is greater than alpha, what would we do? We failed to reject. H naught, that's right. And then, so that's what we actually do. Now let's put this in context of the problem. Which one was our claim? H naught or HA? H naught was the claim. So we can say there is not sufficient evidence reject the claim that the two machines produce bottles with different mean fills.
Wouldn't that be the same?
One thing, let me
Those are rejected.
But to reject the claim, there's not sufficient evidence to reject the not based on it.
Yes, you're right. The same. You're right.
So if we didn't want to test, if we didn't address the claim, would we get protest?
You would get a couple of points off you. Because you need to, yes, you fail to reject, but let's put that in the context of the problem. I mean, the whole purpose of a hypothesis test is to kind of test it and then go back and give like a report, if you will. Think of this last sentence as like your report. I failed to reject. Okay, great. What do you fail to reject? Does that make sense?
Yeah.
I'm just going to advance the slide to see, where did I get that from? There it is there. I guess that's where I got it from, because they have, not continuing that two machines produce bottles. I'm wording it differently. That's why. So,
If we like said there's not sufficient evidence like that, we included that sentence and it was right. We addressed the other thing, other than the claim. Would that be point sign?
so like, are you saying if you put it like this?
Yeah.
No, this would still be right.
Okay.
What I was trying to do there is put it, that's like the slide that would be y'all's technically. Y'all could put that answer and be perfectly fine. Dual credit on their assignments. Hey, let me go back. Wrong way. Their answers, like on their problems, tend to have this format that we wrote it in. I was just trying to hit two birds with one stone, basically. Get them practice hearing it and using it, but then also we're still writing a conclusion as well. As far as AP goes, that would be y'all's official conclusion. There's not convincing evidence that the two machines produce bottles with different fills. Does that make sense? Okay, we ready for the next example? Okay. So now we're going to talk about cold medicine. So in an attempt to determine if two competing brands of cold medicine contain on average the same amount of acetaminophen, 12 different tablets from each of the two competing brands were randomly selected and tested for the amount of acetaminophen which each contains. Totally not related to the problem, but do y'all know the popular brand name for acetaminophen? Tylenol. Yeah. Acetaminophen is the brand name that's popular as Tylenol. Anyways, the results in milligrams follow below. Use a significance level of 0.01 to determine if there's evidence that the brands of cold medicine have the same amount. On average. Okay, so let's get our calculators and as quickly as you can, quickly but accurately, put brand A and brand B into L1 and L2. As quick as you can.
We have to do all the stuff first.
You can do second plus 712. That would. And if someone gets the one variable stats for brand A, let me know and we can fill those in.
Is 497.83.
Okay. Okay.
Deviation 8.830.
Okay. Perfect. Does anyone have brand B yet? I mean, honestly, I don't care where you write them. It may be smart to maybe write them on the top of page 6. That way you don't have to flip back and forth. That's up to you.
Mean is 5.67.
Okay. Got it? Yeah, perfect. Okay, so those are our summary statistics. Now, AP, you would also want to take note of the box plot information that it would give you in the readout if you arrow down. Gives you min, max, and all that, median, all that good stuff, so you can just quickly create a box plot with it to check for normality. Because, I mean, on your assignment, I'm not going to be there saying, okay, let's look at the next slide. See, it's normal. Here's a box plot for you. You're going to have to create that. So that's part of the one variable stats output. It allows you to be able to quickly sketch it and be done with it. I mean, we haven't even defined our hypotheses yet, but we know we're going to need these numbers, so let's just get that out of the way and go from there. Okay, can I get to the next slide? So mu1 is the mean amount of acetaminophen in cold tablet brand A, and mu2 is the mean amount of acetaminophen in cold tablet brand B. Then what can we say about our hypotheses? So our null and the alternative. Which one does the problem give us, the null or the alternative?
Alternative?
It's at the end, or I guess it's actually at the beginning, at the top of page 6. It says to determine if there is statistical evidence that the branded medicines have the same amount.
Oh, so no, that's equal.
They give you the null.
I was reading the wrong spot.
So actually, it's right here. I'm going to just, instead of me writing it, I'll pop it up there. Give us some time. So the null is that mu1 equals mu2. But remember, we need a hypothesized value to plug into our test statistic. So we moved it over. That way we could say, okay, 0 is our hypothesized value. And then what would the alternative be? mu1 is not equal to mu2. Or, equivalently, you could say that mu1 minus mu2 is not equal to 0. Not always. I mean, like you all had a homework assignment yesterday where when you had to write the hypotheses, they weren't 0.
For the second part of it, it totally just flips the values. So when you just make the 10-minute, you just make that 10.
That, and you would also have to change the signs. Okay. So now that we've got our hypotheses done, what's our next step in the process? Can I just start calculating my test statistic? I gotta check my assumptions.
It's small.
So it's a small sample. Here, well, first, we can note that, and you don't have to write the whole paragraph down. If I were like grading a problem, what I would look for AP is for you to say this first part, the samples are randomly selected and independent. So this part I need. And then you could go on to say, since they're not large, we need to test for normality or check for normality. But you don't need to do the normal probability plots. I don't expect y'all to be able to do those. I say be able to. We covered them, but I don't expect y'all to do that on the homework. That's a lot more tedious when the calculator gives you the box plots information. You just have to draw it. So what I do want y'all to do is draw a box plot. You can list it. And you don't have to write a paragraph. You can say like one. Normally, like the way that, honestly, the way I have it on my paper here, instead of all these sentences, I have it like listed one. Random sample, question mark. And then I just say something like sample, basically this. Samples are selected independently and randomly. That's it. And then 2, large, question mark. And I said, ends less than 30, we need to check. Here's my box plots. Here's my conclusion about the box plot. So you can keep it short and sweet as long as you're to the point. Does that make sense?
That's not for us though, right? Like, we don't have to write all that down on a.
Y'all will need to know the assumptions. I can have a matching question or a conceptual question. That's like, which, for this type of problem, which assumptions need to be true? You'll have to know, but you won't have to when you're actually working a problem out.
It's just time sample if it's large, like above or equal to 30.
Yeah. So, like I said, box plots are to me the easiest, being that your calculator gives you the 5 values you need to draw the box plot. It gives us those 5 values. It's just a matter of can we graph them and draw a box. Okay, questions up to the point. Okay, is anyone still trying to get any of this written down before I switch slides? Okay, let's jump into the calculations. We need to set, or I didn't even conclude, I just said, here's a box plot, by the way. But since the box plots are symmetric, if we look, it's about the same distance each direction. Doesn't seem to be much skewness. We can assume normality. Okay, now on to the calculation. So it's always a good idea to write your formula. That way you can see what you need to plug in and where. So we have to do a t-statistic because we have small samples. So x1 bar minus x2 bar.
So T is for small.
T is for small, yes.
Any other reason we need to speed, or is it small?
Small, and then, we don't know sigma.
Only no, no, gotcha.
Yep. So that's the top, and then we have S1 squared divided by N1 plus S2 squared divided by 2. Now we wrote down all of these values already. That's what we got from all the one variable steps we did. Let's plug them in. I have 497.83 minus 515.67 minus, what's our hypothesized value? 0 over square root. And we have our standard deviation, so 8.830 squared over 12 plus 5, no, not 5, 15.144 squared over 12. Okay, so if I calculate this, what would I get? Negative 3.53, that's right. Where did my pen go? There it is. Negative 3.53. So now we need to get p-value. What's that? We can't do that. We have to.
Special equation.
We gotta use a special equation.
What about us?
Y'all, for the sake of this example, we're all gonna do it. But on y'all's homework, once we get through with this, I'm gonna actually talk at the end of today, talk about degrees of freedom for y'all, and then another couple of formulas for y'all.
Alright.
And they're all on your formula chart, so even though it's not in here, not an official example, y'all have them. We just haven't talked about what they are. Okay, so for the p-value, first we need to get degrees of freedom. This kind of starts our p-value section, well. But degrees of freedom is that V formula, so V1 plus V2 squared over V1 squared by N1 minus 1 plus V2 squared over N2 minus 1. We've got to use this formula.
Formulas.
Okay, now the V's. What do the V's stand for? Well, I'll simply put this piece as V1. This piece is V2. Of course, with square roots, but that's V1, that's V2. What's V1 equal to? What's just this first piece equal to? 6.497. What about V2?
V1 and V2 again?
So V1, the actual formula itself is S1 squared divided by N1. V2 is S2 squared minus N2. But what I was pointing out up here is if you notice, under our square root in the test statistic, we really have both V's. That's V1, there's V2. So what would V2 be equal to?
$19.112.
19.112. Okay, so let's take those and plug into our degree of freedom formula. 6.497 plus 19.112 squared over 6.497 squared divided by, and what's our sample size for sample 1? What's N1? 12. 12 minus 1 is 11. Plus, and then we need V2 squared, so 19.112 squared. What's our sample size N2? Well, down N2 minus 1 would also be 11, yes. Draw a little line under here. Okay, so then degrees of freedom, what would we get when we calculate that big old formula? Is it 34.007? I think we're a little high. I feel like we're double what we should be. Yeah. 17.704. Now, for degrees of freedom, what do I have to do? Truncate.
17.
Degree of freedom is 17. Now for our P value. We get to actually compute that now. Well, let's think back to our hypothesis for a second. Is this a one-tailed or two-tailed test?
Two-tailed, because it's equal.
Two-tailed because it's equal. Equal and then not equal. So we're going to need to do 2 times the probability that T is less than negative 3.53.
Are we going to do too much?
Because it's a two-tailed test. So we can only find one tail at a time. But since it's symmetric, we can just multiply that one tail times 2. And that is where your calculator would come in to do the TCDF. And I'm not going to pull it up because it'll take too long to boot up on my computer. But What would be our lower bound in the when we do TCDF? Negative 999. Sounds good. What about the upper bound? That's right. Our test statistic, negative 3.53. And degrees of freedom? 17.
What are the results?
Yes.
Like, when we test, like, which one do we choose?
We run 3 decimal.
Yeah, 3 decimal. So, what did you get when you do your test statistic, or when you do the probability? Sorry.
Zero, zero,
0.001. 2 times 0.001 is what? 002. So there's our p-value. Now I'm out of room on this slide, so I can't write my conclusion here. But how does this compare to our alpha of 0.01? It's less. So what would we do?
I thought it was 0.05.
Is it alpha 0.05?
Wait, no, I was looking at the wrong one.
0.01?
Sorry, Mr. Short, I'm sorry, but like, how did y'all do this after on p-value? Like, I thought you had to go to the t-distribution chart.
So we can't use the t-distribution chart because those are only critical values. We need a totally different chart that y'all don't have. So we did it in the calculator. We did second, bars, and TCDF.
TCDF, and then just what?
And then your lower bound would be negative 999. And then I keep trying to remember, do you have the calculator where it just takes you and says TCDF parentheses and then you gotta type in with all the commas? You'd say negative 999, comma. And then your upper bound, which in this case would be our test statistic, so negative 3.53.
And close parentheses.
Comma, degrees of freedom.
I mean, how do you get the upper bound versus the negative 999? Is that just assumed?
That's the lower bound. Since we want less than our test statistic, we want everything less than. So we just pick a big number.
Okay, so I could have done like negative 500.
Yeah.
Okay. I got you.
You give them negative 5,000. I mean, just a big negative number to make sure it captures everything. Since p-value is less than alpha, what do we do? Do we reject or do we fail to reject?
Good.
We will reject. That's right. Okay, I need to get to the next slide. This is just them getting degrees of freedom. We did that. Okay, there's our p-value. Let's do the AP conclusion this time. It's more wordy, but I did dual credit last time. Let's do AP this time. So since the p-value is less than alpha, we reject H naught, which means the data provides strong evidence that the mean amount of acetaminophen is not the same for both brands. Specifically, there's strong evidence that the average amount per tablet for brand A is less than brand B. You can abbreviate.
I don't like for them to like test and all that.
Well, this last part is just honestly kind of extra.
Okay.
But let's talk about the last part, because when I first read it, when I was doing notes, I'm like, what? How can they conclude that? But if you think about your test statistic, was your test statistic positive or negative?
Negative.
Negative. Remember, that was XA minus XB that we did. If it's negative, that means this one has to be bigger, right? So there's strong evidence that A has less than B. That make sense?
Yes, sir.
So we can even get even more specific based on the fact our test statistic was negative.
There was enough evidence to reject.
Yep. There was enough evidence to reject the claim.
Would it be wrong for us to say there's not enough evidence to suggest that they are wrong?
Honestly, I need to look that up. I don't have a good answer for that. Someone in third period asked the same thing. And at this point, my best explanation would be I would kind of err away from that. Simply because of the fact that the whole goal of hypothesis testing is trying to essentially package up evidence and say, look, I'll have enough evidence to reject your hypothesis. So by us saying that there's enough evidence to, wait, how'd you word it one more time?
There's not enough evidence to suggest they have a safe wrong.
Yeah, so that wording it like that, we have evidence to suggest the other. I see what you're saying. I just don't know that that would come across correctly. Does that make sense? I'll look into it.
So for now, in general, do you want us to address the claim or more address the alternative hypothesis?
I'd like y'all to address the claim, which the claim may be the alternative. If they said less than or greater than, it may be the alternative. But try to always put it in terms of the claim.
Sure.
Uh-huh.
What is that right there? Like, you're saying it provides strong evidence that the mean amount is not the same for both, but that's pretty much saying that it's strong evidence that rejects, right? So the problem, like for me, like I could say, like, the reject the claim that the amount of acetaminophen is the same in both bottles.
Yes, they reject the claim that the amount is the same in both bottles.
Alrighty.
Yes, you may. Any other questions on this one? We're asking good questions, especially when they stump me. Okay, so let's actually switch gears a little bit, talk about confidence intervals. Now, for dual credit, you won't have to really know much about confidence intervals. Your test is on hypothesis testing. Your confidence interval test was the last one you did. So, I won't have to know much about this next part, but just bear with us.
Alrighty.
Because that's all the rest of this section is confidence intervals. Until we get to the end, then I will need to know stuff. Okay, so for a two-sample T confidence interval for the difference between two populations or treatment means, we're going to need to use the same two assumptions. Namely, they have to be independently selected random samples, and the sample sizes have to be large. Or the population has to be at least approximately normal. That's where like our box plots come in, and we're like, they're symmetric, so we can assume normality. It either has to already be large or be approximately normal. If these hold, we can find a confidence interval using this formula. And if you remember back to when we really just focused on confidence intervals, we called this T-crypt. So feel free to evaluate it. Not evaluate. What am I saying? To shorten it. I don't even know where I got it. Oh, that's where I got it. I was trying to say abbreviate instead of evaluate. Wow. Feel free to abbreviate it. Just to make it shorter on you. Now, the T critical value will also be based upon our degree of freedom formula. I realize these are small, so I'm going to rewrite them bigger down here. It's really the same formulas that we've learned before. For degrees of freedom. And just like before, we need to make sure we truncate the degrees of freedom to an integer.
Why is this chapter just two really long sections? That like broken down into.
It's actually 3 sections.
Yeah, really, really long.
Yeah, 3 really long sections. Because they're trying to fit everything for 2 populations into 1 chapter. .3 starts on page, I think it's 13. 14. Anyone still trying to write down the formulas? You got it?
No, I got it.
What you got?
So, like, whenever we solve for the degree of freedom, right? So, like, when we truncate a number, does it mean like basically for the number? Basically,
Does it mean what?
for the number.
For the number, yes. That's exactly what it means. Miss Riley.
I don't know, I was just joking.
Yep, that's exactly what we're doing. We're flooring the number. Okay. for comparisons of two treatments using, for comparisons of two treatments, you really need to have the same assumptions. They need to be randomly assigned to treatments, or vice versa, treatments need to be randomly assigned to them, and the samples need to be either large or approximately normal. Okay, so let's look at an example. Okay. Hold it for a second. Good. Okay. So, just kind of, I don't want to say it's off topic. It's not off topic, but just leading into this example. Have any of y'all noticed that, like, if you sleep less, you tend to eat more? Or do you stay about the same?
Three counts, like when I go to like one, like I'll do like try some before, and I put it, like one, more number.
Gotcha. Gotcha. Yeah. See, for me, I don't know. It really, on average, I tend to eat the same amount, whether I get 8 hours or 4 hours. But what really gets me is when I get no sleep. And I either rather be eating or drinking something pretty frequently, or I'm gonna fall asleep. I've done that in college a time or two, and yeah, anytime I sat, I'd rather have a drink or something with me, because if I don't, I'm going to sleep.
If you were to drink coffee that day.
Well, I really don't drink coffee. I don't like the taste of coffee. But yeah, I drink unsweet tea. Go figure. Okay, anyways. So that's what this study looks at, is whether sleep impacts how many calories you eat in a day. So first they ask us to calculate the mean and standard deviation. Just for the sake of saving time, I'm going to give those to you. So the average for those that get 4 hours of sleep is 39.24. The average for those that get 8 hours of sleep is 4,069.267. Standard deviation for 4 hours is 829.668. Standard deviation for 8 hours, 952.896. Just to save us time from having to put these into L1 and L2. And then we don't really list this on here, but let's go and write it. How many samples are in the first population? 4 hours. 15. What about the 8 hours? Okay, there's our statistics. Is that? Okay. So, you have a question, Will?
Is in the 8, is it also 15?
Yes.
Okay.
They're both 15. Okay. So let's verify our assumptions. So the first one, is it random and independent? Yes. So as far as like what I was saying earlier, straight to the point, you could just do something like this and then say yes, stated in problem. You just verify that assumption. 2. Is it large? Do we have large samples? No. Must verify normality using box plot. And then at that point, you would draw your box plot. And then comment on it and make your conclusion. So, see, I mean, they're kind of wordy. I just tried to keep it. And then you draw this box plot over here. There's your box plot. And then you could say they're approximately symmetric, so it's safe to assume normality.
Where does this go?
This goes under assumptions. Pretty much what I have in red is kind of like the bare minimum. And then, of course, the box plot there. Okay, so let's first we're going to need to get degrees of freedom. And to do that, we need to use our lovely formula that's got V1 and V2. So let's get V1 first. So S4 squared divided by N4. It'll be 829.67. Wait, no, that's not the number we used. Our numbers are slightly different. Let's use our numbers. Our numbers, they rounded some. Our numbers didn't round quite as much. So that's going to make a difference in the final answer. Just FYI. So we said 829.668 squared divided by 15. So that gets us, I'm going to give you all that value for the sake of time. 45,889.93. And then for V2, to be S8 squared over N8. So our not as rounded value is 952.896 over 15. Oh, I gotta square it. That's gonna give us 60,534.05. And then we use these values to get degrees of freedom. Using our lovely formula. 45,889.93 plus 65 squared divided by 45,889.93 over. Now, we need to do N1 minus 1. So each of our N's up here are 15. So 15 minus 1 is 14. And I forgot to square this. Plus 4.5 squared over 14. Again, to save us time on the calculation aspect of it, you should get 27.48, which means when we truncate, or as we'll put it, when we floor the number, what do you get for degrees of freedom? 27. Okay, so to get the T critical value, I'm going to draw a little cutout here. What confidence interval do we need? 95%. So a 95% critical value with 27 degrees of freedom. That gives us a T critical of what? You're looking at it. It is on the tables, yep.
Is it equal? Is H not equal?
not sure if you can do that on the calculator or not. There's probably a way. I just don't know of the way. 2.052. That's right. That's our critical value. Okay, so now let's do our actual interval itself. So it's going to be x bar 4 minus x bar 8 plus or minus the t critical times the square root of S4 squared over n plus S8 squared over plug in our numbers. So 3924 minus 4069.267 plus or minus. I need to drop down to the next line because I'm out of room. 2.052 times the square root of 829.668 squared divided by 15 plus 952.896 squared divided by 15. Again, saving us time. When you calculate all of this out, you would get that your interval is negative 814.68 to 524.15. That's your interval. Will, are you still trying to get it written down, or are you good?
Okay.
You're good? Anyone still trying to get this written down? I actually need to clear the ink off. No, it's gonna be another to the bell one. Okay, so now the interval they give here, they round it to numbers, so it's gonna be different than ours. Here, just so we're consistent, our numbers that we got were negative 814.68 here. And here it's going to be 524.15. So we're 95% confident that the true difference in the mean food intake for two sleep conditions is between those values. Now, notice that 0 is in our confidence interval. Not only is 0 in the middle, it's almost exactly in the middle. So there is not convincing evidence that the food intake would be different. Not convincing evidence that food intake is different. Now, the two examples that we did not get to, they're just more confidence interval examples. So we can get to those a little bit later. What I do want to do is go forward a few slides for dual credit's sake. So dual credit, you may, since there's only like 3 minutes left, maybe you want to get a picture of the slide I'm about to put up. Or just listen. You don't need to get a picture. It's on your formula. We'll do these later. Do that later. Okay, so you know how I told y'all that y'all won't need to know the complicated formula? If you look on, like your homework, for instance, if you still have that out that I gave y'all, what this will say is, come on, where's my pen? This will look like population variances are equal. If they're equal, you simply add your samples together and subtract 2 degrees of freedom. And add the sample sizes together. If population variances are not equal, you take the smaller of the degrees of freedom. So find the degrees of freedom for the first sample, find it for the second, and pick the smaller.
What is population?
Sigma squared. So it'll tell you in the problem, assume population variances are equal. Assume they're not equal. Now, on another note, for dual credit, on the homework, use the middle part of your formula chart for 8.1. Use the bottom part for 8.2. So start using those now. I'll see y'all tomorrow. You too.